Hello guys, welcome on Tesla Adventures. In this video, we are going to discuss the magnetic field due to a coaxial wire system. So I hope you have seen the coaxial wires in the cable wires or something else. So in a coaxial wire system, I'll tell you that there are two cylinders like that, two or more than two cylinders. So one cylinder is carrying some current and the other one is carrying some other current. Okay, so let us suppose that this is the inner cylinder and this is the cross-sectional view of these cylinders. And the inner cylinder is carrying a current of I, and this region complete, which is shaded with this green line. So it is carrying a current I in outward direction. We are considering that current is coming in the outward direction. And the other region, this region, is carrying a current of 2I. And this current is also coming in the outward direction. You can assume that current is going in inside direction or outside direction, anything. You can assume anything. So we have assumed that both of the currents are coming out of the plane, and the current in this shaded region is 2I and the current in this region is I. So we have to find out the magnetic fields at this point, and let us mark the point A, this is B, and this is C. So there are 3 points A, B, C, and we have to find out the magnetic fields due to this system at these 3 points. So first of all, let us talk about point A. So to find out the magnetic field at point A, we have to consider Amperian loop. Let us consider this Amperian loop like that, and this is the Amperian loop, and let us name this loop as loop 1. Let us also, so this is loop 1, and first of all, integration of B dot dl on loop 1 is equal to, now you can see that the total current enclosed in the region inside this loop 1 is 3I. So it will be equal to mu naught into 3I. And the limit of integration in loop 1 is 0 to 2 pi r, 0 to 2 pi r, and r is RA, and here RA is greater than 2R. So B into 2 pi RA is equal to mu naught into 3I, and B is equal to mu naught into 3 mu naught I divided by 2 pi RA. This is the magnetic field at point A. Now let us find out the magnetic field at point B. For that, let us again draw a Amperian loop. So this is a Amperian loop like that, and let us find out the magnetic field at point B. So at point B, let us use a new page. So at point B, we know that RB is greater than R, but obviously RB is less than 2R. So integration of B dot dl for loop 2 will be equal to, loop 2 is this one, inner loop, will be equal to mu naught I inside. Now there is an interesting change in this situation, that I inside is the current completely flowing in this wire, obviously, and the current which is bounded in this region, which is inside this loop. Okay, so this is I, total current, and we have to find out the current in this region. So the total current will be I inside will be equal to I, this is I, and plus. Now you can see that this area, only this area. Now let us use the unitary method. So we know that J current density of outer wire outer wire is equal to 2I upon the area of the outer wire. So area of outer wire is this area, and this area is pi into 2r square minus pi r square. So it is 3 pi r square. So this is J, and the current inside this area, let us name that current as I naught, which is bounded only between R and capital R and small, this RB, this area. So this current will be J outer multiply by this bounded area. So this bounded area will be pi RB square minus R square. So pi RB square is the total area of this loop, and pi R square is the area of this wire. So we are subtracting these two area to find out the area bounded between this inner cylinder and this loop, this area. So I naught will be equal to 2I by 3R square. I have cancelled out capital R, and this is RB square minus R square. This is I naught. So here it will be I naught, and therefore integration b dot dl, limit will be from 0 to 2 pi rb, will be equal to mu naught I plus this current 2I by 3R square. So this is 2I by 3R square and RB square minus R square. So this is RB square minus R square, and this is B into 2 pi R. B is mu naught I is common, so it is 1 plus 2 by 3 into RB square by R square minus 2 by 3 this. So it is equal to mu naught I, and 1 minus 2 by 3 is 1 by 3, so 3 is common. So it is 1 plus 2 RB square by R square is equal to B into 2 pi RB, and B will be equal to mu naught I by 6 pi RB 1 plus 2 RB square by R square. This is the B at point, magnetic field at point P. Okay. Now if we find out the magnetic field at point C, which is inside this inner cylinder, then we have already calculated, we know that at this point the magnetic field would not be due to the current flowing outside this loop. I am drawing the loop. So at this point the magnetic field will be due to only the current inside this loop, this current, and we have already calculated this magnetic field in the previous video. So it would be equal to mu naught J R by 2, where J is J inner. J is equal to the current density of the inner wire. So inner wire current density is I upon pi capital R square. So it is I upon pi capital R square. So B at C will be equal to mu naught I R by 2 pi R square. This is the magnetic field at point C. So this is the coaxial wire field, and this is just an example in which I have taken the currents to be flowing in same direction and different amount of currents. So in any situation you can find out the magnetic field of coaxial wires by using Ampere law. Thank you.